So what do we have now, right? So to summarize, let me put it all these things together and then say where we are right now. We are saying, we started by saying what is the probability that if I start with a random vector u in d dimension and then map it using 1 by square root k r to a lower dimension, I get v, and then I am asking what is the chance that the length of what I obtain is large when compared to the length of the original vector in d dimension. So this was the bad event, and we said this is same as the length of a standard normal Gaussian vector in k dimension being greater than 1 plus epsilon times k, and after all this we are saying that is at most e power, or let me write it, e power minus k epsilon squared by 4, which is a great thing, right? So, so this is saying that I can take any vector, whatever vector that I want in n dimension, apply the JL transform and measure the squared length in the lower dimension, and that deviating by a large amount is going to be upper bounded by e to the minus k epsilon squared by 4. It depends on which is the lower dimension where I finally put it in, project it to, and how much accuracy that I need, which is epsilon squared. Now, how is this going to help us, right? So, again, if you go back and think about what was the statement of the lemma itself, right? I'm going to use a stronger color. So, if you remember, the lemma said, I had n points in RD, and then I map it using 1 by square root k r. I get n points in RK. Now, what have we so far proved, right? So, we have so far proved that if I take any 2 points and then think of the difference vector as my u, right? So, if this is my u and then the corresponding difference vector, this is my v, right? So, what is v? V is just 1 by square root k r u. If I take any fix a single difference vector, then I am saying that single difference vector's length is not going to change by too much, right? So, the chance that it deviates by too much is bounded by e to the minus 8 k epsilon squared by 4. That's something that we have proved. Just to make sure, is this division by 8 or 4? Okay. So small correction, so it does not really matter, but we have to be precise here a little bit more. So, this is going to be 8, that is a small mistake I made. So, this is epsilon squared by 8 minus epsilon squared by 4. So, that is going to be minus epsilon squared by 8, but it does not matter. I think the rate at which it falls with respect to k and epsilon matters more. Anyway, so coming back, so we had this single vector. If I fix any single vector, which is for any 2 points, the difference vector, then if I map it, the length is preserved the bad event happens with at most e to the minus k epsilon squared by 8. That is what we have proved so far. Now, what we want to happen is not for just a single vector. Well, that single vector could be any vector, that's okay, right? So, you can take any fixed vector in U and then this holds, is what we have said so far. But we want this to hold for every pair, right? And we want it to hold for every pair at the same time, right? So, that's the important point to think about, right? So, what we have proved is, if I fix one vector, then that vector's length does not deviate by much, or at least we know a bound on how much it deviates. But we do not want this to happen just for that one vector. So, it is like saying I conduct the experiment for this pair, right. So, and I get the length is preserved. Now, if I separately conduct the experiment for this pair, well, that length will also be preserved. But what I want is, I conduct both experiments together and then both the lengths have to be preserved. It is like, to give an analogy, if I toss a single coin, right, so what is the chance that it will fall heads? Well, that is 50%. If I toss another coin, the chance that it will fall heads is also 50%. But I want both the coins to fall heads, isn't it? So then the chance is 25%. So in other words, a slightly different way of thinking about it here is going to be the following, right? So what we know, what we want, what we really want, what do we really want? What is the real bad event? Let's think about that. The real bad event is if I have n points, I have n choose 2 pairs, and even if for one pair the chance, even if for one pair the distance is not preserved up to 1 plus epsilon, then that's bad for me. So the real bad event is the probability that I care about is probability that there exists a pair xi comma xj such that mxi minus mxj's length squared is greater than or equal to 1 plus epsilon times xi minus xj squared. This is the actual bad event, right? So we care about, right? So this is the real bad event we care about. Why do I say that? So if this event does not occur, what's the complement of this event, right? So if this is a bad event, the complement should be good, right? So what is the complement of this? This is saying even if one pair has deviates, right, so in length by a large amount, then that's bad for me, which means the complement is all the pairs, for all the pairs the distances are preserved up to 1 plus epsilon, which is the good event, right? So which means now we want to bound the probability of the bad event, right? So in other words, we want to bound the probability that there exists a pair such that this bad thing happens. Now this is same as saying probability that union over all pairs, this event happens, mxi minus mxj squared greater than 1 plus epsilon xi minus xj, right? So there is some chance that xi minus xj might deviate. There is some other chance that xj minus xk might deviate. Now I am saying I want the union of all these bad events put together is the bad event for me, right? So now what I am going to do is I am just going to think of these pairs as separate vectors, right? So every pair is a different vector, and then I am asking out of these n choose 2 pairs, right? So I want the chance that the union of all these pairs, right? So n choose 2 pairs, mxi minus mxj's norm squared is greater than whatever 1 plus epsilon xj, right? So that's the union that I care about. Okay, let's go back. Now what I'll do is I'll kind of apply the union bound here, right? So the union bound will say, if you remember, this is at most the sum over all pairs ij n choose 2 pairs, the probability that xi minus xj squared is greater than, or mxi minus mxj squared is greater than 1 plus epsilon xi minus xj squared. This comes from union bound. Right. So I want the union of bad events to be the actual bad event that I care about, but I don't have a good way to talk about the intersection of these events and so on. So I am just going to loosely think of each of these bad events as separate bad events and completely ignoring the intersections, which means I am upper bounding, right. So probability of A union B is actually probability of A plus probability of B minus probability of A intersection B. But then if I ignore the intersection, then it is at most A probability of A plus probability of B, and this generalizes for n events. In this case there are n choose 2 events, where it goes wrong for each of these individual xi minus xj's, and there are n choose 2 of them, the chance that at least one of them goes wrong is the sum of the chance that each of them goes wrong. Is bounded by, it's not equal to, is upper bounded by the sum of the chance that each of them goes wrong. But then for each of them going wrong, there is nothing special about the specific xi or xj, it is just any vector, right. So, I can just think of this as some vector u, and then this is the corresponding v that we have, right. So, for any fixed vector, it can be any arbitrary vector, fixed vector, we have already proved the chance for this, right. So, which means that we go back and say that, hey, for any fixed vector I know this is the chance, and then if all the pairs have to be should be within the range that we want. So, then I am just adding it up n square times, rather n choose 2 times, but then we will be loose here, and then we will say this is at most n square times e power minus k epsilon squared by 8, right. Why? Because the bad chance of a bad event for any fixed vector and xi comma xi minus xj in particular, you can take any ij and then you can think of xi minus xj as that fixed vector, and for that we already is bounded by, we have already proved that it is bounded by k e power k epsilon squared by 8. So, basically then we want the probability of the real bad event that none of the pairs, for no pair the deviation is large, is n square times the chance that for a fixed pair the deviation is large, because there are n squared events, right, possible events, and you do not want any of these to go wrong. We are just doing an union bound. So, this is the final probability that we have, right. Now, let us say, I mean, this is n squared e to the minus k epsilon squared by 8, whatever this number is, right. So, let us say we want to make statement like the probability that no pair, let me write it in English, no pair squared length deviates by more than 1 plus epsilon is at most, let us say 0.001. I want to make a statement like this, right. So, I want to make statements where I plug in some value 0.001 or some value. So, and then I want to be this confident about my low dimensional embedding. So, which means that I will take this value as some delta, I mean it can be 0.001, in general let us say it is delta, and then I want to make such statement. So, what I have done is, so far what we have proved is the probability of the real bad event is at most n squared e to the minus k epsilon squared by 8, and then we want to say that, well, this guy is something like epsilon, delta, right. So, where delta is whatever value that I as an implementer of this algorithm is going to pick, right. So, let us say this is less than or equal to delta is what we want. So, now what does this tell us, right. So, we want for this to be satisfied, we want n squared e minus k epsilon squared by 8 is at most delta. Take log on both sides. So, that will be log n squared minus k epsilon squared by 8 is less than log delta. Log is monotonic, so the less than or equal to stays, which implies k epsilon squared by 8. I can even set this to equal to, it does not matter, okay. So, k epsilon squared by 8 is greater than or equal to log n squared minus log delta, which is just log of n squared by delta. So, which means then we have the final statement that if k is greater than 8 by epsilon squared log n squared by delta, right. So, this is delta and this is, should not seem like an 8, yeah. So, this is the final statement that we have, right. So, if I want all pairs to be preserved in terms of distance for an accuracy of 1 plus epsilon, so then what we are saying is, if I want this to make such a statement with very high probability, where the deviation probability, where the error probability is delta, then I have to choose k such that k is something like 8 over epsilon squared log n squared by delta, right. So, so this is the final statement of the JL lemma, right. So, what we have managed to prove is that, if I have n points in whatever arbitrary dimension and I do a simple, super simple 1 by square root k R transformation, where R is just standard Gaussian, and if I choose k, right. So, earlier whatever we have said so far did not matter what k I chose, but now I have to make a choice for k, right. So, if k is too small, that is, if it is less than 8 by epsilon squared log n squared by delta, then I can't make a statement that all n square distances are going to be preserved with, with up to 1 plus epsilon with high probability, right. The high probability is at least 1 minus delta, because delta is the probability of the bad event. So, the good event is at least 1 minus delta. So, I cannot be sure if I choose k less than this. On the other hand, if I choose k equal to or greater than this, then I am sure that, with overwhelming probability, that is, with probability greater than or equal to 1 minus delta. If delta is 0.001, then which means that with probability greater than or equal to 0.999, I can be sure that, all the pairs of distances, the lengths are preserved up to 1 plus epsilon factor. That is the power of that, power of the JL lemma, right. So, we have managed to prove a high probability bound, and again I can't reiterate how the importance of this does not depend on D, the original dimension, right. So, which is the great fact about this lemma, right. So, no matter which dimension you start with, if you have a low dimension which depends only on the number of data points and the accuracy to which you need it, then you are still okay, right. So, that is the power of this lemma. Of course, log n squared, though it is log n squared, I can think of this as just, I can think of this as log n times some constant. So, this whole thing k is just order of the main things that matter is log n by delta by epsilon squared. Yeah, sometimes the delta is also treated as a constant high probability thing. So, we typically think of this as log n by epsilon squared. K is in log n by epsilon squared, where it is implied that we are talking about a high probability statement. Of course, we cannot guarantee it always. There will always be some bad event that might happen, but then the chance that happens is very, very less, right. So that is the JL lemma for us, right. So, it's a wonderful lemma, and I can't state how important it is when you are dealing with scale, because if all you care about is distances, which is what most of the times we care about when we do machine learning, pairwise distances for nearest neighbors or whatever algorithm that we have, you can blindly apply JL lemma, reduce the dimension, and then run your algorithm on the reduced dimensional space. So, which means that the algorithms will be much faster computationally, right. So, we are dealing with algorithms for data science at scale, and then this is like a cornerstone or the central piece of how you can attack scale in a very, very simple way, right. So, algorithmically it is super simple, right. So, all this analysis might seem complicated, and if you are seeing it for the first time might seem very overwhelming, but algorithmically speaking there is nothing really going on, right. So, you take any vector that is given to you, high dimension, learnt, not learnt, given to you directly, whatever it is, do a random mapping projection using Gaussian matrices, scale it carefully with 1 by square root k, there you go, right. So, now you have new set of vectors which have distance properties very similar to the original. In fact, there is more you can say, right. So, we are not going to talk about this in this course, but it is not just the distance, but the angles are also preserved, and angles sometimes are very important for machine learning, right. So, you will look at dot products and between vectors and then make decisions, whether it lies on one side of the line, other side of the line, etc., etc. The angles between the vectors are also preserved with high probability. We won't prove that, but that's another fact of the JL lemma. The other thing that we did not prove is that we only proved the bad event on one side, right. So, that is the length of the vector after I do the random projection is greater than or equal to 1 plus epsilon times k. So, let me say that similar analysis can be done to show again the probability that v squared is less than or equal to 1 minus epsilon times u squared, which means that this is also a bad event, right. So, that the length is too small than what you expect. This is also less than e to the minus k epsilon squared by 8, right. So, you can do exactly, I mean almost similar analysis. I mean small changes in terms of signs, etc., might have to be taken care of, but then the same, you write it as e to the lambda, do Markov, and then do a slightly different Taylor series expansion, and then you will hit something very similar, right. So, this can also be shown. Now, well, again, if I want both of these to hold together, right. So, this is one bad event which is bounded by e to the minus k epsilon squared by 8. There is another bad event which is bounded by e to the minus k epsilon squared by 8. On the higher side, the length being too much is a bad event, the length being too small is also a bad event. Both these bad events happen with probability e to the minus k epsilon squared by 8. Now, if you want both of these bad events not to happen, then the chance that at least one of them happens is a bad event. So, which means then you will get both of these together to hold will be which is to say the probability that v squared is less than 1 minus epsilon u squared, or v squared is greater than or equal to 1 plus epsilon u squared. So, this is either this event happens or this event happens, right. So, it is a union of both events, right. So, now which means I can apply a union bound. I can say that this is at most the probability that v squared less than 1 minus epsilon u squared plus the probability that v squared greater than or equal to 1 minus epsilon u squared. But then we know both these probabilities we have already, I mean we showed one, the other is similar to show, is basically okay, this is less than or equal to 2 e power minus k epsilon squared by 8. Now, if this is for a fixed vector, again we can ask if this has to happen for all n squared vectors. So, the probability that the real bad event maybe I should call it real bad event, because this is in fact what the lemma is saying, real bad event where the length is preserved on both sides for all n squared pairs is at most 2 n squared e to the minus k epsilon squared by 8. And now, if you want this to be less than or equal to delta for some choice of delta, then this will imply k is greater than or equal to maybe there is an extra 2 somewhere sitting here, that is what it will end up being, right. So, 8 by epsilon squared log 2 n squared by delta, that is all it will be, right. So, this is not 8, this is delta. Yeah. So, which is in terms of order nothing changes, there is just one extra constant that gets added. So, k is still order of log n by epsilon squared. So, yeah, so that is the Johnson's Lindenstrass lemma's proof, right. So, as I said, it is a powerful technique and it is a very simple idea.